Hello and welcome to CS264 Software Design. This is week 10 and lecture 19. And in this lecture, we're going to be working with software design patterns again, and in particular, we're going to be looking at some of the structural pattern set. We're going to learn about the Gang of 4 structural software design patterns, and we'll see one of these patterns in detail. It's going to be the adapter pattern. We see how we can implement it in C# and also with Java using an example that we're familiar with. Okay, once again, I will be basing much of the work on this design patterns book and site. It's the refactoring.guru website. And specifically, you can check out the refactoring.guru design pattern section for lots of information on all of the design patterns in the Gang of 4 suite, and also for lots of examples in C# and other object-oriented languages as well, of course. As I said, I bought this version of the book for €10. It's really good. I love this book, and I'd certainly recommend it. But you don't have to buy the book. Lots of the material is on the website itself, and certainly worth checking out. Anyway, it's really, really good for this work. Okay, so we have looked at the creational patterns already, and now we want to look at the structural software design patterns. So these patterns are concerned with describing how objects and classes can be combined and form a large structure, and that is designed by identifying a simple way to realize relationships between entities. So it's about how we put together all of the classes that we need for our application in a way that eases our design, a really nice way for making all the classes work together. There are 7 structural design patterns in the Gang of 4 list. Adapter, which we'll see in this lecture. Bridge, which we'll see in the next lecture. Composite, decorator, facade, flyweight, and proxy. Okay? And all of these patterns are designed by considering a class's structure and composition. Okay? The main goal of these structural design patterns is to increase the functionality of the class or the classes involved without significantly changing the composition of the class or classes. So you'll see that there's a significant difference here from the creational design patterns that we saw last time. They have been designed for class instantiation. Everything's about instantiation. And the behavioral patterns, we haven't seen these in detail yet, but you have seen some because you saw Memento and you work with Memento and you work with Command. These have been designed around class communication with other classes. So, you can see there's this clear distinction between the 3 kinds of, or classes of design pattern: creational, structural, and behavioral. So the structural patterns provide an established solutions to the most commonly encountered problems in all of software development. In fact, you're going to be using some of this stuff already. You'll be using it, may not even realize that you're using a pattern. Software development teams, or you yourself, can select and utilize appropriate design patterns, not just the structural ones, actually. In order to maintain a uniform, clean, easy to comprehend, and maintainable code base. And these are the reasons we want to use patterns everywhere, not just the structural design ones. So remember Christopher Alexander, I mentioned him earlier. He gave us the whole notion of pattern languages in architecture and landscaping, all that, a language for describing patterns. He tells us that, in short, no pattern is an isolated entity. Each pattern can exist in the world only to the extent that it is supported by other patterns. So the larger patterns in which it's embedded, the patterns of the same size that surround it, and the smaller patterns which are embedded in it. Okay, so we live in a world of patterns. Okay? And software, of course, as well, is all about patterns. There are large patterns, there are deployment patterns. We saw the ones like Model View Controller, then there's patterns that sit within a class almost, and there are patterns, within a collection of classes, and there's patterns across the whole application. Also, each pattern describes a problem which occurs over and over again in our environment, and then describes the core of the solution to that problem in a way that you can use the solution 1,000,000 times over without ever doing the same way twice. Okay, so that's really, really important. The pattern is like this template. Okay, it isn't actually a piece of code that you just copy and paste. A lot of the time you'll give some ways of doing or implementing the pattern, and we see that in the next lecture when we look at Bridge. So it would be a good idea to remember these important points here, when thinking about structural and all the other design patterns, of course. But for us, it's nice to have this with structure. So when do we use a structural pattern? So we saw the last time we looked at the creational patterns, and we said, well, we'll use these because we don't want to be using or calling the new class constructor, everywhere or anywhere. Okay, we wanted to control how we use new. So that keyword can be a real problem when it comes to object-oriented design and development. So what's the story with software then? With structural design patterns and software design. So these patterns are concerned with managing the connections between objects. So when we use these patterns, when one or more object communicates with another object or objects. So remember that the creational patterns all fulfill the exact same fundamental purpose. We provide a new object. That's the whole purpose of the creational ones. Structural patterns are unified in essentially or form a group in that they're all about communication. They're fundamentally different, of course. And they may work the same. And in fact, later on, maybe when we look at bridge, you'll see that the bridge might look like some of the other patterns, okay, but we use them in different ways. It's important, I guess, that you don't confuse structural design patterns with data structures. Okay? Data structures are static entities, whereas structural design patterns also specify the methods that connect the objects, not just the references between the objects. So structural design patterns describe how data are arranged and how data move through a pattern. Structural class patterns use inheritance to combine the interfaces or implementations of multiple classes, and structural object patterns use object composition to combine the implementations of multiple objects. They can combine the interfaces of all the composed objects into one unified interface, or they can provide a completely separate or new interface. Okay? So remember, we have structural class patterns and we have structural object patterns. Sometimes it's important to really single out the differences here. Okay, so the Gang of Four structural design patterns list. What are they? So I mentioned some already, okay? These design patterns describe how to assemble objects and classes into larger structures while keeping the structures flexible and efficient. So the first one we want to think about is facade, okay? And facade is a unified and simplified interface that allows easy and consistent access to a set of interfaces of a subsystem. It's a single class that represents an entire subsystem. Flyweight, the pattern makes object usage easier and more efficient and is also concerned with sharing variable details. Proxy, the proxy pattern uses one object to represent another object. So a proxy object which serves to access another object in some controlled way. Sometimes, for example, you might have a local object, like a connection to a database or connection to some service, and that would represent the connection, if you like, that's represented by some other object somewhere else. So proxies are really, really useful. Okay? There's another one called private class data, and this pattern restricts the accessor or mutator access by controlling right access to class attributes, separates the data from the methods that use it, and also encapsulates class data initialization. So accessor and mutator are your getter and setter methods, of course. It's worthwhile checking out this book on design patterns. As I said, lots of the definitions are explained in more detail if you go into that book. Really important, that I'm just giving you a summary here. You need to look at the actual individual patterns, so go to the website and check it out. Lots of examples there as well. So adapter makes things work after they're designed, okay? Bridge, for example, makes things work before they are designed. That's why in this lecture later we look at adapter, and then in the next lecture we look at bridge, and you can see the general approaches to utilizing the design patterns with the two, even though they're both structural design patterns. And remember, it's about how all these objects are going to communicate with each other. It isn't really, about creating objects like we saw with the creational patterns. So bridge then, it's designed upfront, okay? It lets the abstraction and the implementation vary independently, okay? And we'll see more about that later. And adapter is retrofitted to make unrelated classes work together. Now that's a nice distinction between the two. Adapter provides a different interface to its subject. Proxy provides the same interface, and decorator provides an enhanced interface. Decorator allows us to, improve an object, if you like, or change an object by adding more functionality or removing functionality. Okay. Adapter changes an object's interface. Decorator enhances an object's responsibilities, and decorator is more transparent to the client. So as a consequence, decorator supports recursive composition, and that is impossible with pure adapters. So you might be thinking, well, what are the limitations of adapters? Well, that's why we have decorator. So composite, one of the other patterns, and decorator, they have very similar structure diagrams and reflect the fact that both rely on recursive composition to organize an open-ended number of objects. And again, you should have a look at the book and you can read and see examples of all of these. Some other rules of thumb, and probably these are really useful for you after you become familiar with some of the patterns. So this is just giving you a summary of those. And you might be saying to yourself, well, let's look at this one. Composite can let you compose a mediator out of smaller pieces through recursive composition. And you say, well, I don't know what mediator is. Well, you could look at, one of the behavioral patterns, for example. Composite, I haven't looked at this in detail. So this is meant to motivate you to go and look at some of these. Okay, so composite can be traversed with an iterator, visitor pattern that can apply to an operation over a composite. Composite could use chain of responsibility to let components access global properties through the parent. You could also use decorator to override these properties on parts of a composition. It could use observer to tie one object structure to another, and it could use state to let a component change its behavior as its state changes. So we're seeing lots of different patterns here, okay, about things we might want to do with objects as part of our solution. When we design classes, here's a pattern composite, here's a pattern visitor, chain of responsibility, decorator, observer, state. These are all patterns, mediator, strategy. These are all patterns that we need to become familiar with. And really, we can't really talk about patterns in isolation. And you might say, well, I don't know about all of these. Well, of course, you don't know about them, and we haven't looked at them here in lectures. But I would recommend that you actually read a book and go and find out some more about these patterns. We don't have time to do all of them in any amount of detail, but remember, there are choices about which pattern you will use. You have choices about the way they use and interact with other patterns, and it's up to you as a designer to decide on the best use of the patterns, and best use of selections of patterns for your actual solutions. Okay, so this is a complex paragraph here, and the reason it's here is to give you some insight into the fact that using patterns is a complex process. Okay, decorator, that lets you change the skin of an object. Okay, and strategy lets you change the guts of an object. Okay, so they're interesting as well. You might be thinking, well, how does this happen? And the questions you should be asking yourself, well, what does changing the skin of an object mean? Or what does changing the guts of an object mean? Well, skin of an object is probably the interface, strategy makes the implementation, and it allows, so you might say, well, how does decorator, what are the similarities between decorator and strategy? So you could try that yourself and have a look. So decorator is designed to let you add responsibilities to objects without subclassing, and that's a really important thing as well, because sometimes we don't want to be doing too many subclasses, because it becomes unwieldy. The composite's focus is not on embellishment but on representation, and these intents are distinct but complementary. Consequently, composite and decorator are often used in concert together. Okay, so this slide really, in terms of the rules of thumb, is the sort of thing that you could think about looking at when you finish the course. Come back and revisit this slide, and then look at the book, and then maybe look at some other books and try to understand, how all of these patterns come together, okay, in terms of design, because it's about decisions that you make. These are not solutions. They give you guidance really on how you can form solutions. So the decorator and proxy patterns, they have different purposes, but they have similar structures. They both describe how to provide a level of interaction to another object, and the implementations keep a reference to the object to which they forward requests. Okay? Facade, as it implies, defines a new interface. Adapter reuses an old interface. So an adapter makes two existing interfaces work together as opposed to defining an entirely new one. Okay? Facade objects are actually often singletons, because only one facade object is required. So you can see that there is this interrelationship between this structural pattern facade and this creational pattern singleton. Mediator, okay, is similar to facade in that it abstracts functionality of existing classes. The mediator abstracts or centralizes arbitrary communication between colleague objects. It routinely adds value, and it's known or referenced by the colleague objects. Contrast facade, that defines a much simpler interface to a subsystem. It doesn't add any new functionality, is not known to the subsystem classes. Right, so we can continue with these rules of thumb, really, and we can see that there are more patterns. The more we look at the patterns, do we see that there's more relationship with the earlier patterns that we've looked at and the later patterns, which come in terms of behavior. We've also seen some of those already as well. So the abstract factory, for example, can be used as an alternative to facade, the high platform specific classes. And this is really interesting because we're saying here that we can actually have a couple of approaches here. So we can use this structural design pattern called facade, okay, to hide platform specific classes, or we can actually use a creational pattern to do it. So it isn't just a case that here that we have a situation when we come to design that we just use the structural ones for one part and then we use the creational ones for another part. Sometimes we can actually use the creational in place of structural, okay, or the other way around if we want, okay. Flyweight shows you how to make lots of little objects. Facade shows you how to make one big single object that represents an entire subsystem, okay. And again, the patterns don't happen or work in isolation. Flyweight is combined with composite to implement shared leaf nodes, and Flyweight explains when and how state objects can be shared. So really, I guess the point in all of this is to remember that the structural patterns are concerned with how classes and objects can be composed to form larger structures. Okay? The patterns have been created after years of experience. You may not have the experience yourself, so don't worry about that. Really, don't worry about that. With experience, you'll become more familiar with the patterns. It may take years because it depends on the kind of work you do. You may only encounter a couple of patterns. You may only be working with, one set of patterns, creational. You may be working with structural patterns only. You may, there's lots and lots of scenarios here. Use I guess the lecture and these particular slides, to think about jumping off and looking into a textbook and finding out a little bit more about all of the various patterns and how they interrelate with each other. Not just enough to know the individual patterns, although you do need to know some of the patterns in detail, but you should have a sense of how all those patterns work together and how they interact. And that's what makes study in software design patterns so complex and sometimes so difficult, in fact. And later on, when you have to make choices yourself, you really need to understand why you are making those choices, and you also need to be able to understand why you have made those choices and whether they worked, and test those. And it's good, and with practice, to be able to look at code and say, what pattern am I using here? Can I use a different pattern? Is it the best pattern? Is it a workable pattern? Will it scale? And you can just become a better developer, of course, a better designer at that point. Okay, so we're going to look at a pattern, one of the patterns. I've talked about, two in particular. I said, that we could look at the adapter pattern. Allows us to work with existing objects, and we could look at the bridge pattern, which we do next lecture, which looks at designing. So it allows us to be able to design some set of classes first. But adapter, okay, so it's an intermediary between two classes, converting the interface of one class so it can be used with the other class. So we can look at the UML here. There's a really nice example of this at this website here, gofpatterns.com, gang4patterns.com. And they have a nice description of all 7 of the patterns, in fact. I'm just looking at this UML diagram from the adapter pattern. This is a classic UML description here. And in fact, we'll see that, there are variants on this, but this is the one you'll see lots of places, okay? We can see this uses here, and this notation here. We have some client, which could be just your program. It has a target, which is an abstract class, and it has a method here, request, which is a void type here. This basically implements an interface that's known to all clients. And then we have an adapter. Okay, so the client talks to the target. Your adapter basically allows us to be able to sit between the target and the adaptee. Okay, and we see the target, inherits here our adapter. Okay. Again, look at gofpatterns.com. It's nice. Okay, so the adapter pattern acts as intermediary between the two classes, converts the interface of one class so it can be used with another class. It enables the classes with incompatible interfaces to work together. Okay, and that's nice. The adapter pattern implements an interface known to its clients and provides access to an instance of a class that's not known to its clients. An adapter object provides the functionality of an interface without having to know the class used to implement that interface. Okay, so this is where this is where it all happens. Okay. Again, I'd recommend you have a look at this as an alternative to the textbook that I recommended earlier. And so the adapter pattern implements this interface known to clients. Again, provides access to the instance of a class that's not known. So in the diagram here, we can see adapter client. Here, that's the code client. Okay? Adapter is the adapter class that actually forwards the calls to the adaptee. Adaptee here is the old code that needs to be adapted, and target is the new interface to support. And this is sometimes called a wrapper. Okay, sometimes called a wrapper. And this again is essentially the same UML diagram here. Okay, and you can just go back between the two. Okay, you can see that we have these service here, which is the older service with an adapter that looks at that service, and then it implements this interface here. Okay, which we've seen here. Adapter is implementing target, and we have some service. Okay, so you will see different descriptions here as you work through the examples in the various book. This one again, back to our Dive into Design Patterns book or on the website, refactoring.guru. But the object, we talked before about the fact that you might have object adapter implementations and class adapter implementations where you're trying to reuse an object or you're trying to reuse a class. Okay, for example, we might have some singleton that's there we want and it's represented as a class. There are no real object as such, or maybe the object is hidden within the class itself. So sometimes we have to look at both. The object adapter, this is the object adapter here, they use the object composition principle. Okay, object composition principle. The adapter implements the interface of one object and wraps the other one, and it can be implemented in all popular programming languages, all the OOP languages. We have a client here, we have an adapter that's adapting, implementing some client interface here for some service. The class adapter implementation they use inheritance. Okay, so we have a notion of actually using object composition or object inheritance. So what happens here in class adapters is that the adapter inherits interfaces from both objects at the same time. Okay, and that can really only be implemented in programming languages that support multiple inheritances, such as C++. Okay, so if you check out this link here, you'll find some information if you go to this link here and look at the C++. It's nice. Definitely worth examining. Okay, and you can look at this one here again. The client class contains the business logic of your program. The client interface describes the protocol that other classes must follow to be able to collaborate the code. The service, usually a third-party legacy code. The client can't actually use it directly because of the incompatible interface. And then we have an adapter, and that's the class that works with both the client and the service. It implements the client interface while wrapping the service object. Adapter receives calls from the client via the adapter interface and translates them into call that can be wrapped. The wrapped service object can understand. And then remember here, what's important is that the client code doesn't get coupled to the concrete adapter class, as it works with the adapter via the client interface. Okay, this interface here. Okay, it's not built into the client here. Okay, so it's really nice to be able to see that. Okay, let's have a look at a demo. Okay, and I have some demo code that we can use here for you as well. Okay, so it's a really excellent summary of all of the design patterns together with some nice code at this website here, Design Patterns, Structural Patterns of Design Classes and Objects. Okay, and it's from this author, Trung and Dang, and I really like it. Okay, and this is a nice, simple example of the adapter. So essentially, we have some real-world examples. There are some real-world examples, of course, in the Dive into Design Patterns. Some of them are long, the copy, and they tend to be duplicates of the actual classes. But there's some brilliant work there, and of course, you have all the other languages as well. But this provides some nice shorter links. Okay, so they're Java actually. Sorry, I forgot to say that these are all Java examples. And it's worthwhile, you know, if you just want to make some connection with Java as well, because you're familiar with both. So what I've done is I've small error in the code if you implement it, but it's easy to pick up. You know, you'll fix it yourself. But I've actually, I'm probably showing the Java code running as well here, as well as the C# code. So I've reworked this example code into C# code, and we can run this and see. So you know, it can be easily converted from C# to from Java to C#. It's no problem at all doing this. Okay, so all of the patterns that we've looked at can apply to Java. And I've taken this example from here. It was a Java program. I've made it into myadapter.cs, and you can see that as an example. I'll show you after this. Here's the example. Okay, so what we want to do is we want to actually build essentially an adapter that converts from 100 volts, from 220 volts to 100 volt. Okay, so it's like a physical adapter. So we're requesting 100 volt from this socket. Okay, that's our specific request, and we're going to use the adapter to make the change in the voltage. Essentially, could be so. You could do this with software, of course, as well. Okay, so the original power is 220. It needs to be adapted to 100 in order to work. So this example code here, so if you can click on the link, you'll find the code that solves the problem. It defines a high voltage plug, which is the adapter here, a plug interface, which is the target, okay, and an adapter plug, which is the adapter, okay, and it implements these in software. I have this done, yeah. So let's go here and have a look at this. So if you look, I have produced one my adapter and my bridge. We talk about bridge in the next lecture. So my adapter's here, so we can go into this and have a look at the code. So you can just, I have it in open Visual Studio Code as well. So let's have a peek here. Here's my adapter. Okay. So this is the C# program. Okay, so I've got my adapter. So I have an interface called plug. Okay, and that has a single a method called recharge, which returns an int. Okay, and then we have a high voltage plug. Okay, and that allows us to return 220 volts. And then we have a class adapter plug, which implements this interface plug here. You can see this. Okay, and what it does really is it implements recharge here by creating a high voltage plug called big plug, and then we actually call the recharge method on this to get the actual voltage because it returns 220, and we subtract 100 volts from this and we return this, so we get 100 volts. Our client then is very straightforward. It's our program, if you like, and really this is just a header here. So now our high voltage plug is our old plug, and we're creating a new high voltage plug, and we can call this old plug.recharge, and we see we've got too much voltage because we're really interested in 100 volts rather than 220. So now what we do is we create a new plug, which is the adapter plug, and that adapter plug, then that adapter plug then allows us to be able to get the charge, and it'll be 100 volts. Now there's a bit of a, because this is, you know, a contrived example, if you like. Normally we would not have access to the high voltage plug, or, you know, in this class, you know, that we wouldn't be using that in our actual client program, our adapter client here. We would just be dealing with the adapter. Okay, I'm just showing you this for the example, and also because it was done in the Java examples as well. So let's run this. So we can see this is our 220 is too much voltage, adapter into 100 voltage. So these were the examples here. So that was too much voltage, and that's what's called here because we were just calling the original piece of code, which, you know, the whole point of the adapter is because we don't actually have access to or can't call it directly, but we're simulating that in this particular example here. Okay. I mean, I remember when I was, when I was a student and I was writing, I was studying physics and I was writing adapters all the time, because we would be trying to, you would have, well, we'd be trying to have hardware controllers, for example. And sometimes we could have basically used proxy patterns in addition to this as well. But what we would have been doing is I'd have been trying to capture information from sensors that would have very specific pieces of software associated with them, and you couldn't really do anything with that. You couldn't hack them. They'd come with pieces of programs that would just provide you with the information, and so those would only run at operating system level or something. So one of the things I would have done in terms of adapters would be this would have been under Windows DOS kind of, and we're talking a long, long time ago, and back in the late 1980s, for example. So we wouldn't have had Windows even at that point. So we would write software that would create an instance, if you like, of the program running, and then we would wrap that with commands. And so you'd write a wrapper, or essentially an adapter that would pass the commands back and forth, and then we would make that work for us. And then we would write programs. I would write programs in whatever it was, Turbo C at the time, or Pascal, or we might only have applications that would provide a hardware interface via machine code. We would probably access that and wrap the machine code. So all the time you were trying to work with different kinds of sensors, and maybe you might buy a new sensor that would come with new hardware controller, new software controller specifically for that, and you need to swap between them. So writing adapters was just a way of life when you were trying to do some work at that point. And those low level work, you might write a card, for example, that works, and you might have so you might build a card, you plug into your computer that controls a telescope or something like this, controls some sensor, and then you just have to write adapters that will work all the time. So it just became a way of doing work, and you essentially, but you couldn't actually do this within your program. Maybe I remember I moved from writing software in Turbo Pascal, up to some C. I worked from there, and then one language after another, but we still were able to retain the original hardware controllers in the assembly language, for example. So anyway, so this happens all the time. It's a very, very useful thing to do. But the point, I guess, is that we couldn't do this line here. We had to use and write everything through the adapter. The reason we have this here is just for demo purposes. I mentioned already that this particular example came from Java in this website here. So let's have a look at the Java. So we implemented Java as plug.java, the high voltage plug.java. You'll notice it's very similar. The adapter plug.java, very slightly different, but pretty much the exact same. And the adapter client here, which is public class adapter client, and it is pretty much the exact same as your C#. Okay, let's have a look at running that program. Actually, it's called adapter client, so I can just compile this, do it here. Using Javac. Okay, and now we can run the application. So we'll know that it actually created the classes for us here: adapter class, adapter plug.class, high voltage plug.class, and so we should be able to just run this now. Okay, we can run this using Java adapter client, and it works fine. Okay, actually, I'm going to run my .NET. Actually, well, let's run the Java one again. The Java one is running much faster than the .NET one, isn't it? Something to bear in mind. I might never noticed that before, but it seems to be actually running a bit faster. Okay, so look, I guess the example here is that we can make the adapter. We create this adapter that wraps around the adaptee. In this, for our examples here, we just wrote the adaptee as well, so it was no problem. Okay, let's get back to this. Okay, so the structural patterns actually include some quite sophisticated and powerful techniques. Okay, they are primarily based on two basic approaches: delegation and object composition. So these are the two terms you need to remember when you're looking at structure and talking about structural patterns. With delegation, the pattern is one in which a given object provides an interface to a set of operations. The actual completion of those operations, however, is performed by one or more other objects. With object composition, other objects are stored as pointers or references inside the object that provides the interface to the clients. So object composition now is a really powerful OOP technique worth remembering. The structural design patterns show you how to take an advantage of object composition. So when one class hands off a task to another class, that's delegation. That's, composition, for example. With inheritance, each child is a part of another class or classes. With composition, however, objects may use or utilize other class or classes to complete a series of tasks. And most design patterns include both shallow inheritance and also composition. Okay, so it's important that you understand the differences between these. Okay, inheritance, we talk about shallow inheritance so that you don't have lots and lots and lots of layers of hierarchies here. Okay, you prefer shallow inheritance and composition to extended inheritance hierarchies. Okay, so when do we use the structural patterns? We talked about this earlier. Okay, so if you want to add a new function, this is a kind of checklist for you. You can say to yourself, when you're doing your work, your analysis of your code, and you say, I wonder, should I use a structural pattern here? So these are the questions you might ask, and then it tells you what pattern you should consider looking at. So this is a nice tip, and you can actually have a look. Some of this you'll see on the GOF patterns website, so you can have a look, and you may find more as well. So, and this certainly isn't an exhaustive list. If you want to add new functionality dynamically to existing objects or remove it, use the decorator pattern. If you want to control access to an object, use the proxy pattern. If you want to create expensive objects on demand, use the proxy. Want to enable development of the interface and an implementation of a component to proceed independently, use a bridge. If you want to match otherwise incompatible interfaces, use adapter. And we saw that in the last example. We'll see bridge in the next lecture. If you want to reduce the cost of working with large numbers of very small objects, then use flyweight. If you want to reorganize a system with many subsystems into identifiable layers with single entry points, use facade. If you want to select or switch implementations at runtime, you can also use bridge. If you want to simplify the interface to a complex subsystem, you can use facade. If you want to treat single objects and composite objects in the exact same way, use composite. So it's a really useful list. In other words, there's two ways of thinking about this. Here are my patterns. What can I do with these patterns? Or here's my issue. Which pattern should I consider using? And it's important that you understand going both ways. Okay. Right. Short lecture really, but today we learned about the Gang of Four structural software design patterns, and we were introduced to the adapter pattern, and we saw examples of its implementation using both C# and Java. Thank you very much for watching lecture 19.